As a graduate student, I get really specialized training in how to do a very specific type of research. The Engage program gave me another type of training that graduate students rarely get. I learned how to talk about my science in a way that is engaging, enlightening, and informative. You can learn more about our innovative program at engage-science.com. And I get to have this opportunity because of the special collaboration between Town Hall and the UW's Engage program. Together they host a series called UW Science Now as part of the Seattle Science Lectures. Sponsors include Microsoft and KPLU. I would also like to mention that the best way to keep up with Town Hall's program is to become a member. Membership offers downfront seating, discounts on book and ticket purchases, a mailed copy of Town Hall's monthly calendar, and it provides the support essential to bringing you more than 400 events annually at affordable ticket prices. Tonight's speaker program will run about 25 minutes, including 5 minutes for your questions. We ask that you come to the mics at the edge of the stage here and over there, so we can pick you up on the recording that we're making. Before I introduce our guest, though, I'd like to mention some other events happening at Town Hall. First of all, please join us tonight for Rebecca West, who will blend interior design with marital counseling in her talk, Conflict-Free Home Makeovers at 7:30, following this Engage talk. Also, although this is the last talk of our 2016 UW Science Now speaker series, we will be here at Town Hall next year and hope to see you all again for another great round of Engage talks. And now to our main speaker. Studying Earth's geological and atmospheric history is crucial to understanding how our modern climate will respond to the rapid increase in atmospheric carbon dioxide. Enter UW Earth and Space Sciences graduate student Julia Kelson, whose research focuses on ancient global warming events by studying preserved soils and lakes. How much warming can we expect in the future? Kelson will explore how a period in Earth's history with similar amounts of carbon dioxide in the air can be used to predict the outcome of this century's climate change. Please give a warm welcome to Julia Kelson.
All right, thanks for the introduction, Jason, and thanks all of you for coming out to Seattle Town Hall on this beautiful evening to listen to me talk about ancient soil and the work that I'm doing to better inform global warming. And so climate change has garnered a lot of attention in the media. Just the other week, this was on the front page of the New York Times, is this really striking image of the heat wave in India, and scientists have predicted that climate events like this one will become more intense and more common with climate change and global warming in the future. You can also readily find dramatic images of glaciers like this one and ice sheets in the Arctic and the Antarctic that are experiencing increasing melting and will continue to melt in response to global warming. A little bit closer to home, Washington and California and most of the West is experiencing drought, and this can be depicted with images like this one where we have reservoirs that should be full but are half empty, and you see these exposed shorelines. And this lack of water resources is affecting many people. And it's also, these droughts will tend to become more intense and more common as global warming continues. And they also make the landscape more susceptible to things like wildfires, like this one in California. And this directly affects people, like many of my family members, who are forced to evacuate their homes due to impending fire danger. And so while these effects of climate change are extremely dramatic in the media, and they will continue to become more intense and more common in the future, climate change to scientists can look a little bit more dry. And so this is what global warming might look like to a scientist, where this is time on this axis, with 1400 starting here and the 1900 and 1998 here, and an increasing average temperature on this axis. And this is a classic graph that was one of the first in 1988, where scientists realized that we could actually measure climate change within our with certainty. And this graph is become known as the hockey stick graph for its apparent similarity to a hockey stick, where from about 1400 all the way until the Industrial Revolution, you see more or less constant temperatures. And then as soon as humans enter the scene, you see a dramatic increase in temperatures and a spike in temperatures. So scientists have been able to measure within our certainty that the Earth is warming. And we're also able to measure, and we also have a really good understanding of the physical processes that are causing the climate to warm. And we know that greenhouse gases in the atmosphere are warming the Earth's surface. The Earth has this nice atmosphere that surrounds it and protects it from space, and the atmosphere is made out of gases like carbon dioxide, nitrogen, and other greenhouse gases. And most of our heat comes from the sun. And that heat, that incoming solar heat, is able to pass easily through the atmosphere and enter the Earth's surface and warm the Earth's surface. However, when it hits the surface of the Earth, it changes form, and when it tries to radiate or reflect back out towards space, it can no longer penetrate through that atmosphere. It can no longer exit the atmosphere. So our atmosphere is kind of like a one-way blanket where it lets solar heat in, but it doesn't let solar heat out. And as you increase the greenhouse concentration in the atmosphere, you actually make that blanket a little bit thicker and a little bit more effective, so that with the constant heat coming into the atmosphere, we don't lose as much heat and we can continue to warm the surface of the Earth. So we are able to effectively measure climate change, and we understand the basic process that includes climate change. However, the ability to quantitatively predict how the Earth will respond to this global warming remains elusive. So what about future climate change? On this graph, again, I have time going this direction, and this is the hockey stick information repeated down here. And many scientists are working on trying to understand and trying to predict exactly what the Earth will do. And climate predictions can be this dramatic, where by 2300 we might see something like 22 degrees Fahrenheit of climate change. And to put that into perspective, Seattle has a mean annual temperature, or throughout the year, the average temperature is about 54 degrees Fahrenheit. Someplace like Miami has an average temperature of 77 degrees Fahrenheit. So by 2300, this graph suggests that someplace like Seattle will actually have a climate as warm as Miami, which is pretty dramatic. However, there's a lot of uncertainty in these predictions and a lot of unknowns because it's a chaotic system. So we could sit around and wait until 2300 and see what happens to climate. However, I think a more effective approach, or one of the many effective approaches to better predicting this future climate change, is by looking at past events of climate change that we can use as analogies for what we think future climate will be like. So my research approach is to use the past as the key to the future. We can look at periods of the ancient Earth history as an example or an analog for what we think modern global warming will do to the Earth's surface. And so we can go shopping through the climate of the ancient past for periods where we think the climate was warm. And on this graph, again, I have time on this axis, but I've changed the time to be millions of years instead of hundreds of years, which is a good trick that geologists often use. And this is deep ocean temperature, approximate deep ocean temperature on the y-axis. And dinosaurs are about here to put this deep time into perspective. They went extinct about 65 million years ago. And we're here in the Industrial Revolution. It's just this tiny little blip. And to put the modern warming and modern time into perspective, it would just be that tiny little square at the end, where the hockey stick is a relatively small amount of warming that we've experienced so far compared to the amounts of warming that Earth has experienced in the past. And to me, one of the interesting parts about the climate of the ancient past is this period of extreme warming known as the early Eocene climatic optimum. And I'm pointing to this obtuse extended period of warmth that occurred about 50 million years ago. And this period of time is interesting because of its extreme warmth. It can be used as a pretty good analogy for what we think the climate of the Earth can be like when it gets warmer. And a couple of things about this time period, the early Eocene climatic optimum, to give you a qualitative sense for how warm this was. Now, there's actually ice sheets at the poles in Antarctica and Greenland have ice in them. 50 million years ago, instead of ice, there was palm trees and alligators near the poles. And you can actually find palm trees, fossilized palm trees, on Chuckanut Drive in Bellingham. So if you're looking for an afternoon field trip, go looking for these palm leaves on Chuckanut Drive. And they're a good example of how warm the climate was, even as far north as Bellingham. It was warm enough to support palms, which are pretty fuzzy plants that don't like frost at all. And also during the early Eocene climatic optimum, there were high concentrations of greenhouse gases in the atmosphere, in the air. And those greenhouse gases acted as a really thick blanket to ensure that the Earth was warm during that time period. And there was about just more than twice as much carbon dioxide in the atmosphere then as there is today. Also, fun fact, in the early Eocene, there were miniature horses like this picture of an eohippus. They're about the size of a fox or a dog. They're pretty tiny. And scientists think that horses were small, kind of like penguins at the equator are small today to be able to deal with the heat as compared to penguins at the poles that were warm. So horses actually got small in order to manage that heat. Another thing that we do know about the early Eocene climatic optimum is that warming of the ocean has been relatively well measured. And so this was the graph that I showed you earlier with the climate over the past 70 million years has been relatively well measured. And scientists have measured it by drilling cores into the bottom of the seafloor and using those sediments to measure, or using those rocks to measure the temperature. And specifically for the Eocene, we have over 40 sites throughout the ocean. So we know fairly well what the temperature of the ocean was during this time period. What we don't know is what the warming over land was like. There's been approximately one location, and this is Wyoming, where people have measured the temperature of the air during the Eocene. Only one location. And to me, this is the most important part of the Earth because that's where I live. I live on land, and barring rapid evolution towards becoming a mermaid or a merman, I'm going to continue to live on land. So I think it's really important to understand how North America will respond to global warming. And additionally, climate on land is much more variable than it is in the ocean. I'm sure you're aware that the climate in Spokane is fairly different from the climate in Seattle, even though it's a relatively small different distance, because there's things like mountain ranges that can dramatically change climate. So if we have just one point of information that can tell us about ancient climate or climate during the Eocene, that's not really enough to give us a feel for how the Earth can respond to ancient climate. And so I'd like to ask the question and then answer it eventually of how hot did it get last time, but how hot did it get in these many different environments across North America? And another question that I can start to address is what about seasons? So there's this hypothesis that during periods of time where there's a lot of greenhouse gases in the atmosphere kind of acted like a beer koozie would act for your beer. So while you could take a cold beer out to a warm environment and your beer will stay cold, or if you so choose, you could take your warm beer out to a cold environment and keep your beer warm. That greenhouse climates will keep the Earth warm or cool during changing seasons, and that we won't see quite the dramatic swing in winter and summer temperatures as we see during periods with less greenhouse gases in the atmosphere. So I think these questions are important. We'd like to know how hot it was during the Eocene and what seasons were like during the Eocene. But unfortunately, while there were alligators and mini horses running around, they weren't measuring the temperature. And even if they were measuring temperature, they weren't writing it down for us to know. So we have to be a little bit more creative or a little bit more clever about how we can go about measuring temperature in the Eocene. And for me, the answer is in ancient soils. So ancient soils, just like modern soils, form at the very, very surface of the Earth. So if there's a change in temperature, or if it rains more, or if there's more sun, the soils will actually remember that information and record that information in their chemistry. And so as a geologist, we can go back and sample those soils and learn something about the climate of the past from these soils. And so this is an example of what an ancient soil looks like in the field. This is Montana, and I'm referring to these bands of color that are on this side of this hill here on this mountain. And each of those bands of color is an ancient soil that used to be on the surface and recorded the temperature during that time period. Here's another example of what an ancient soil looks like. This one is in Big Bend, Texas. And these are these really dark red bands of color like that one, and this red in the foreground. And again, each of these is its individual soil that's recording the temperature and can tell me something about climate during the Eocene. However, accessing these soils can be manual labor, including lots of digging. So this is myself and a field mate digging for those soils to make sure that we're actually sampling the ancient Eocene soil rather than the modern soil. It can also require a lot of wandering around and looking for ancient soil in extreme heat. So we were in Big Bend and it was over 100 degrees Fahrenheit just a couple weeks ago. No shade, no wind, a lot of exposure. And it was really good training to be thinking about warm climates during the Eocene and trying to imagine a world where it would be even warmer than the climate that we were experiencing there. And then, of course, more digging for soil, lots and lots of digging. And so it turns out that to actually extract the information from this soil, you have to look really, really closely at it. You can't just grab the rock and it won't tell you the temperature. And you have to look at this mineral, or one way is to look at this mineral called calcite or calcium carbonate, and it grows in the soil. As the soil is forming, this mineral is growing and growing and growing, and it's recording climate the same way that the soil is growing. And so in the soil, it doesn't look like this beautiful gem shop example. It looks something like this, where it's this little white nugget of information that's growing in the soil. And it can be as big as a baseball or as small as your fingernail. And these are, again, growing with the soil. And what's so useful about this, or in order to explain what's so useful about this mineral, I'm gonna have to put on my geeky geochemistry hat and explain a little bit of high school and college chemistry. So bear with me with this. So to start, calcite has this chemical composition where it has one calcium atom hanging out, a carbon atom, and 3 oxygen atoms. And so let's look at this carbon atom more specifically. So what makes a carbon atom is that it has 6 protons. And usually, hanging out with those 6 protons in the nucleus, there's 6 neutrons. And there's also about 6 electrons that are rolling around the outside. But for my work, I don't really care about the electrons, so I'm going to remove them and simplify the picture. And so this is what a normal carbon atom looks like, with 6 neutrons and 6 protons, and it has a mass of 12. Sometimes an extra neutron finds its way into the nucleus, and so now in this example on the right, we have 7 neutrons and 6 protons for a total mass of 13. And this is what you call an isotope. It's an atom of the same number of protons, but with an extra neutron in it. And all atoms come in these different flavors or different isotopes. So I just explained that carbon can have a mass of 12 or can have a mass of 13. Similarly, oxygen can have a mass of 16 or it can have a mass of 18 if it gets 2 extra neutrons that sneak its way into the nucleus. And these 2 types of atoms are important and useful when they find their way into the mineral calcite that I just discussed that we can find in these soils. So this is, again, the chemical composition of calcite, and usually a molecule of calcite looks like this, where it has all of the light isotopes in the molecule. Sometimes you get a heavy oxygen in the molecule. You can also get a heavy carbon in the molecule. And the world is a really energetic, chaotic place. So while this is a static drawing, what's actually happening is that all of these bonds are wiggling, and they're wiggling really fast. And they're moving with a lot of energy. And you can imagine that if you put a weight onto the end of that wiggling bond, it's a little bit more comfortable and a little bit more stable. And atoms feel the same way. So if you put a heavy isotope or one of these 13s or 18s into the molecule, it's actually a more comfortable position and a more stable position. And it's even more comfortable if you have both of the heavy isotopes in that atom. However, because the world is so chaotic, the atom or the molecule can really only get comfortable in cool temperatures. So you see that you have increasing clumping with cool temperatures. So at normal temperatures, you get most of your molecules look like this one, where you have only light isotopes. And then some of the molecules look like this one, where you might have one heavy isotope, one heavy oxygen, and you might have one heavy carbon hanging out over here. But as temperatures get cooler, you're going to see more and more that the carbon and oxygen are bonded together in one molecule. And that's what we call a clumped isotope, or a clumped molecule. And that molecule will occur more and more with cooler temperatures. So it's kind of like a magnet that turns on with colder temperatures. And those molecules can actually attract to each other slightly better in cooler temperatures. And so as a scientist, I can measure that clumping in my molecule, and I can use this relationship to understand what the real temperature was when that molecule was forming. So again, we'll see increasing clumping at lower temperatures. However, you have to remember that in the field, I'm starting with this little white nugget, and it's not as simple as it might seem to get from this little white nugget into a temperature measurement. And like all good science, it requires a lot of liquid nitrogen and safety glasses and a homemade robot. So this is something that our lab manager has built to produce a temperature measurement. We put the white information nugget of calcite in on this side, and after about a day of analysis and time on a machine, you get a temperature measurement. And so similar workers have used this approach. I mentioned that people have measured temperature during the Eocene in Wyoming, and this is really the one measurement during the Eocene that we have. And now the mean annual average temperature is about 46 degrees Fahrenheit. Then it was about 7 degrees Fahrenheit. So we know that it was much, much warmer. However, I will be measuring it in Texas, so maybe in a month or maybe in a year you can ask me and I'll be able to tell you exactly what the mean annual temperature was in Texas. And eventually, we're looking to measure temperature in many different environments across the world in the Eocene, and also to address seasons. So this is my way of taking a crack at climate change. I'm using ancient soils to better inform what the temperature was like in the past, which can help us inform what the temperature might be like in the future. And these temperature predictions will eventually help us actually adapt to a changing climate rather than just be frightened by these dramatic media images. And what can you do to help climate change? A couple of things. You could buy a bikini and wait for sun, wait for Seattle to turn into Miami weather by hanging out at Golden Gardens. You could learn how to ride a miniature pony, or more realistically, you should reduce your fossil fuel footprint. And with that, I'd like to thank Town Hall for offering me the opportunity to speak tonight, and the Engage program for teaching me so much about science communication, our excellent instructors, Shelly and Robin. Thank you guys. And my many funding sources, the Geological Society of America, the Quaternary Research Center, University of Washington Earth and Space Sciences, the National Science Foundation, and the University of Washington ISO Lab. And with that, I'll take any questions you might have.
Okay, so my question is, how are you going to address the question of seasons and looking at a temperature range many, many years ago? And how do you resolve a 1-year temperature change versus maybe just noise in your temperature data?
All right, thanks for the question. So there are a couple of good questions. The first question is, how am I actually going to measure seasons in the soil? So of course I've simplified my methods for this talk. And the method that I explained to you, the clumped isotope method in measuring carbonates, actually gives you a summer temperature, not a mean annual temperature. And there are other proxies that you can use in the soil that are largely empirical proxies. So people have measured what the chemical composition of the soil was like and compare that to modern soil. And you can use that empirical relationship to get a mean annual temperature. And so if we can measure the mean annual temperature with these other empirical proxies and then the absolute temperature, or the absolute summer temperature using clumped isotopes, that together gives you a range in temperature that is seasonality. And so that's how we're going to measure seasonality. And then the other question is, how do you resolve annual changes in temperature? And so the answer to that is that a soil actually records up to, Jason and I were just talking, up to apparently a million years in each soil profile, usually more like thousands of years. So the soil doesn't actually see a single hot year, but it sees many, many hot years and records that hot temperature. So if there's any really small changes, any small fluctuations, the soil won't record that information.
I'm looking at, if you look at the plateaus like in Wyoming, and there's red and there's lighter color, what is the different color? Does that indicate more heat if it's red or bluish in color by looking at the soil? Because people have painted it, and I'm wondering if that indicates like a long span of temperature.
Mm-hmm. Yeah, so the question is, does the color of the soil tell you something about the temperature? And the answer is yes, but qualitatively. So a red soil, like the ones that I was showing you in Texas and like the ones in the plateaus, in the Colorado Plateau, is in conditions that are oxidizing. And so they'll have precipitation and then an oxidizing event, and that tells you something about the temperature, as compared to a reducing environment where you would get blue soils that are going to be covered, like saturated in water for most of the year. And that can tell you something else about the environment, but not directly temperature.
Thank you for the permission. My first question is about our greenhouse effect. Please just mind. Our atmosphere consists of 3 main particles: nitrogen, oxygen, and carbon dioxide. You know, and we know, they weight of nitrogen is low. The weight of oxygen is middle. And the weight of particles of carbon dioxide is very heaviest. And I'm surprised. Can you explain us how carbon dioxide particles can move up and form greenhouse screen above our atmosphere? I am really surprised. It is my first question. For second question, please bring back the picture about atmosphere greenhouse effect.
You mean this one?
Yes. So, my second question is, if we on Earth, if we have really greenhouse screen around the Earth, so according to law of physics, the heat coming from our soul to Earth must be stopped at greenhouse screen. Greenhouse screen don't permit our heat go into cosmos, and this screen must protect us from solar heat, because this greenhouse screen is working in two directions. Do you understand me? Thank you.
Yeah, okay, so a couple of questions. The first question is, how does carbon dioxide rise to the top of the atmosphere?
Moving up and up.
Given its weight. So I'm not an expert in atmospheric dynamics, but I do know that the atmosphere is fairly well mixed. So just like if carbon dioxide were actually the heaviest gas and didn't move anywhere, right now we would be breathing only carbon dioxide and we wouldn't be able to survive. So the gases in the atmosphere actually mix fairly well throughout the entire column, despite their masses. And it's, I think, because the difference in mass isn't that great. The second question that you have is, how does solar heat get through this greenhouse gas atmosphere? And to answer that question, I have to get a little bit more technical, and it has to do with the wavelength of this heat, or of the heat of the solar radiation, and the waveform that it's in when it passes through the atmosphere. And so when it comes through, it's in one form and one wavelength. And so CO2, or carbon dioxide, actually doesn't absorb that energy when it's in that wavelength. And then when it hits the Earth's surface, the Earth absorbs it, and then it turns it into something called black body radiation. And I encourage you to go home tonight and look up black body radiation. And when that black body radiation leaves the Earth, it actually has a different wavelength, or a different energy form from that of when it entered the Earth's atmosphere. And carbon dioxide has an absorption band that conveniently absorbs the wavelength of black body radiation. So that heat is able to pass through the atmosphere, but it is really effectively absorbed because of that change in wavelength. It's effectively absorbed on its way out. And there's many, I encourage you to go home and look this up. You can look up black body radiation, greenhouse gas effect, solar radiation, wavelengths. These are all keywords that I encourage you to go home and look up for a better answer and more thorough explanation with wavelength spectrum and absorption spectrum graphs, because those will be fairly convincing.
I think with your chart showing the temperatures would suggest that we've got a lot of water captured in the ice, and that in the historical record that you're looking at, I would expect to see sea levels significantly higher. I thought I saw a chart suggesting we're kind of at one of the the peaks of sea level. Can you explain the difference?
I think the difference is the time scale that you are considering. So we could be at a relatively high period of sea level compared to what's known as the Little Ice Age, where there was a period of climate relative cooling in the Middle Ages, but that's hundreds of years ago. And I'm looking at on the time scale of millions of years ago, like during the Eocene. You're completely correct that if there was no ice sheets, sea level must have been dramatically higher than it was today. So, and compared to geologic time, sea level now is actually quite low. but compared to human history, it's actually on the high end because we've seen relative increasing warming since the Little Ice Age. All right, there's no more questions. Thank you guys for coming. Appreciate your attendance.